We are going to start. Eu fico aqui. Então, boa tarde a todos. Muito obrigada pela presença. Prazer enorme hoje ter o professor Schaltegger aqui para poder compartilhar um pouquinho com a gente do vasto conhecimento que ele tem com a geocronologia urânio-chumbo. Urs, thank you so much for accepting our invitation, for being here. Really appreciate it. I'm going to give you a brief introduction about Professor Urs. So, Urs Schaltegger is an emeritus professor at the University of Geneva, Switzerland. His main research interests are in advancing high-precision UPB geochronology of zircon and other ancestral minerals to determine precise timescales of orogenic and magmatic processes in the Earth's crust, and to reconstruct the amplitude and rates of climate change in the geological past and the relationship to large igneous provinces. He is a scientific editor of geology and co-editor of a planet thematic issue of elements. He's a fellow of the Mineralogical Society of America and Geochemistry, fellow of the Geochemical Society and the European Association of Geochemistry. In 2021, has been awarded the Bunsen Medal of the European Geoscience Union. So please, Urs, thank you very much.
Thank you, Brenda, for the introduction. And thanks to Brenda and Valdesir for inviting me here. It's a pleasure, first time in Brazil, and hopefully not the last time. And I was kind of asked, more or less, about this title, so trying to, I don't know whether you see the,
Yeah.
Maybe I take nevertheless the stick. To compare TIMS uranium-lead geochronology with laser ablation ICP-MS geochronology. And the reason is that of course, I spent my life with this here, and since a few years ago I started to do more laser ablation dating, and of course also would like to push this technique to something more precise and accurate. So I do a lot of work. Of course, I did thank the whole isotope group in Geneva during 25 years. I got so much support, and also now more recently, the petrology group in Lausanne. And what we see here is Fleschowitze, one of the reference materials. I'm quite sure you know those who do laser dating, also here in Sao Paulo, and it will come up several times in my talk. And this is a zircon from alkaline melts, which intruded into granulite facies gneisses. Okay, so I will first start with some background. I think just to make sure that everybody knows what I'm speaking about, and then I will speak about these two techniques. So first about TIMS, uranium-lead geochronology, and then secondly about the laser ablation. And I will cover a bit of the same problems, like the preparation, sample selection preparation for TIMS, chemical aberration. You will see what this is, precision and accuracy, how to present and interpret data, and some limitations of the technique, and do the same for laser ablation. So preparation of the samples, which is imaging, how we use standards, precision and accuracy, and also presenting and interpreting, and what are the limitations. And then eventually come up with some examples comparing the two techniques. Let's see what kind of conclusions we will draw. So the background, very simple. We look at the decay of 238 uranium over the green intermediate daughters, and for those who were last week in Iguazu, I apologize, some slides are redundant, I know. So this green decay ends up with 206 lead, with 8 alpha decays, and then the lead 235 uranium decays via the yellow intermediate daughters, 23207 lead, 7 alpha decays. And this is kind of the summary is the decay of 238 over many intermediate, so 8 alpha decays to the ultimate daughter, stable radiogenic daughter of 206. So those people who do U-series dating, they use the intermediate daughters here to make geochronology, and we work with Zircon and old rocks. We use just the parent and the ultimate daughter, and kind of integrate the rest in between. And then I want to show up the workflow of the two techniques. So this is the workflow of chemical ablation TIMS. So we have to separate somehow our zircon, which either is classical with hammer, or we can also have polished sections and take the zircons directly from the section. But we have to isolate them at some point and end up with a polished half grain. We can also already use in situ techniques to get, why not, the uranium lead age already by here, or oxygen isotopes, hafnium isotopes, trace elements already at that stage. But then we eventually take out the zircon from our mount. We do chemical ablation, what we will see in a minute what this is. Dissolve it, separate uranium lead from the rest, and then we analyze this. This is a tracer we have added, of course. We analyze this using thermal ionization mass spectrometry. And we also have the trace element fraction, which in old days we poured away down the sink. Nowadays we can use this and do also trace element ratios, and also again hafnium isotope analysis if we want. So important points is that this step of chemical ablation, which I will get back to, so this consists of two steps. We will see this annealing at high temperatures and then partial dissolution. And the other important point is that there is a step which is called isotope dilution. We add a tracer. We know very well the concentration and isotopic composition of this. We have a precise isotope ratio analysis, which is TIMS, thermal ionization mass spectrometry. And we can deal with lowest volumes and lowest abundances. So we can measure a picogram of lead at the precision of per mils or better in lead isotope ratio. And this is the workflow of laser ablation ICP-MS dating, which is fundamentally different. You know this probably also. This is, we have a laser ablation, so we have a laser beam. Where is the laser? Here's the laser. We direct the laser onto our mount with our polished zircons. We ablate material, so there's really fragments ablated, which get transported by a flow of argon and nitrogen into a plasma, 8,000 Kelvin, ionized, and then transferred from ambient pressures into a high vacuum into a mass spectrometer, where we analyze isotope composition. So this can be a quadrupole, which is shown here, Q, or a sector field ICP-MS, which would be an element sector field, single collector ICP-MS, or a multi-collector ICP-MS, a Neptune. Okay, just one word. What is the difference between precision and accuracy? Because this is essential, and students usually are not so 100% sure what is the difference. So let's look at this compilation here. So you can imagine when you shoot, what you want to hit is that you have, how many are these? 6 shots in the center, highest precision, highest accuracy. They're all together, all in the center. But in the beginning, when you have a new gun, you have to calibrate the gun. That's also, you have to calibrate the laser, you have to calibrate the machine. So this is high precision, but bad accuracy. So accuracy is the offset from the true value, whatever the true value is. When we speak now in terms of analysis, this is a precise and accurate result, because we know we pretend that we know the true value. This is a precise but inaccurate result. And then we have here an example for low precision and low accuracy, so a lot of spread off the center. So when we make an average here of these, we calculate an average of these analyses, we are off the true value, we are wrong, inaccurate, and we have a large uncertainty. Here we are kind of overlapping with the true value. We have still low precision, but we have moderate, so Shaney called this moderate accuracy. But it's overlapping within some uncertainty. The value is overlapping. And then we now compare the two analyses. So any in situ technique, SIMS, secondary, so ion probe, or laser ablation ICP-MS, we speak about a single spot uncertainty of several percent, maybe a weighted mean uncertainty of 1%. When we go to TIMS, chemical ablation TIMS, we speak about single fragment or single crystal uncertainty of 0.5 to 2 per mil, and a weighted mean uncertainty of 0.02%, so 0.2 per mil. So we are factor of 10, at least a factor of 10 better. So these are the three techniques. So SIMS, secondary ion mass spectrometry, laser ablation, TIMS. You see, this is clear why this is precise, because the volume of a zircon we analyze is by far bigger than the volume of an ion probe pit. And the laser ablation is somewhere in between. Actually, we are now, with the smallest sample we can analyze with TIMS, we are about at the same volumes as with laser, but with laser ablation, but with enormously higher background of analytical work. So I will now speak first about this and then about this. And I have completely ignored the SIMS, first of all, because I know you have a world-renowned SIMS lab here, and I am not sufficiently competent that I would dare to speak about this in this context here. Okay. So we deal with a complex isotopic system. So these are three grains of zircon imaged with cathodoluminescence. These are the famous, this is the famous Concordia diagram. So 206 radiogenic over 238 uranium, 207 radiogenic over 235 uranium. So any zircon where the two H's are identical would lay on this line. And now we have zircons which have lead loss. And when you look carefully at your CL images, you see that many zircons kind of have this flurry attitude, and parts of the grains here are white. So I kind of termed coined this term of white thickness, which is now used by some people. So these are areas of the grain which underwent maybe dissolution precipitation, reprecipitation, or recrystallization. We actually don't really know. But when I see such grains, I smell they will have lead loss. Should not shoot with the laser onto such grains. And then we have zircons which have a clear inheritance. So this is an inherited core, maybe, I don't know, maybe two. First one here, second one here, and then a magmatic growth zone, a late growth zone with high uranium. So they may lie on a discordia line up to the age of the inherited component. We also know. And then we have the growth zone, a late overprint with lead loss. We get somewhere in between of all these. So we have at least three components which are defining our system. So such grains we want to avoid, as also such grains when we do TIMS. But with the laser we can separate these different events. Now we have a highly complex mineral with complex isotopic system. Okay, so let's start with the chemical aberration TIMS. So first point is already the worst. It's purely subjective. I select the best grains, or Maria selects the best grains. So which are the best grains? So these are a few. These are quite transparent. Probably we will take these two. This one has a dark core. This one has dark areas in the grain. We probably would not take this. It's a purely subjective first choice and is actually quite, how to say, is quite determining already, because we will have data finally from these two grains and imply that we understand the systematics of our sample, of our Zircon population, on the basis of the grains we have selected. They're not representative. And then we have to deal with the decay damage. So every alpha decay from the first uranium parent to the last stable radiogenic daughter, every alpha decay will produce a damage in the lattice. So the 238 uranium is decaying via alpha, this is the alpha particle, and the first daughter is 234 thorium, and which will travel a bit away, so it's not anymore on the stoichiometric site, it's an interstitial site, and this transfer here, only if it's only 35 nanometers, will create a lot of damage. So Freckle defects are just damages. So every of these decays will create a damage, and when you put this in a when you quantify this in a diagram, this is 100% fully ordered zircon, so 0 damage. This is 100% fully amorphous, so 100% damage. Your zircons will align along a curve, and you can overlay such data with models of, so direct amorphization model, double overlap model. These are models coming from the material sciences, and you see that kind of when you are below a certain threshold, you like to have such zircons for analysis. So the least damaged zircon you would try to find for your analysis. But sometimes you're also not successful. So what we will try, we can define two thresholds. So one is about the 2.5 times 10 to 18 alpha decays per gram, which is here, is called the first percolation point. And the second one is about at 8, so here, which is around, so 8 times 10 to the 18 alpha decays per gram. So here, these zircons we can still repair. We do a treatment, annealing, to repair the intact part of the grain, and we dissolve the more damaged part of the grain. And this is called chemical ablation. This is this process we are using with every single grain. First, we anneal it at 950 degrees for 2 days, and we repair the parts of the grain which have some damage, and then we dissolve away the parts of the grain which had more damage. So we end up with a zircon which hopefully represents only material at the first percolation point, which will hopefully give us an answer which represents the growth age of the material. And we can even quantify this and control this using Raman spectrometry. So this is the Raman shift. This is the position of the main band for zircon, is 2008, and this is the full width at half maximum. So this means the width of the Raman of this peak. And zircons who undergo decay damage, they will follow this trend, the radiation damage trend, and then we do annealing. So with this, the annealed parts will follow this trend here, induced thermal recovery trend, but we will not manage to get up too much. But then we dissolve away the rest. And with the remnants here, we hope to get as close as possible to pristine zircon. And this we do empirically without really, you cannot do Raman spectrometry for each grain before you do the chemical ablation and afterwards. It's impossible. So we kind of do this empirically and hope that it works. And it works maybe, 95%, but not 100%. And to obtain this famous highest precision we have is TIMS, we have to quickly look at this diagram. So the magic number or value is the radiogenic lead over common lead ratio you have in your analysis. So you have a big zircon, a lot of radiogenic lead, a lowest blank possible. You have a very high radiogenic to common ratio. And when you look at the percentage of the uncertainty of a 206 to 38 H, so here you would have one factor taking all the uncertainty you produce. Here you would have two factors equal participating in the uncertainty you produce here. So when we see in the blue area, we have the main reason of the uncertainty is the lead blank. So this is an area where the isotope composition of the lead blank and the low radiogenic to common ratio is producing making the lead blank the most important source of uncertainty. And the limit is about somewhere at 15 to 20. So radiogenic to common ratio of 15 and 20. And when you are higher, so either with very low blank or with very old grains or very high uranium grains, then the blank composition gets less and less important, but the fractionation in the mass spec gets the important factor. So what you can do here, you can improve the blank. What you can do here to control the fractionation is to use the double lead, double uranium spec to control fractionation during analysis. And we do this in Geneva, like in many other labs in the world, using Earth time tracer solutions, which are calibrated in different places and are kind of represent the most accurately calibrated tracer solutions in the world. And then we have some disadvantages. IDTIMS is not just a solution for everything. So one is inherited coarse. Clearly, we do not want to have mixed grains. But one is also that, in any case, the TIMS H is IDTIMS H is a bulk analysis from a grain which is integrating a history of growth. So we can assume that zircon is crystallizing over time in a magma. So when we look at this distribution of dates here, this is what 600,000 years of age difference between the oldest and the youngest grain, and we may see this in a CL image. We see that this is a center of the vein, which is not an inherited core. It's just crystallized a bit earlier in the same magmatic system, got resorbed, overgrown by a sector 2, resorbed again, overgrown by a sector 3, or by a zone 3, and then at the very end you have a thin overgrowth of very high uranium zircon, which is number 4. So when we have a really, really good luck, we may find one crystal who only consists of one. One crystal only consists of 2, of 3, of 4, etc. But in normal case we have mixtures. So all these mixtures will make produce a dispersion of H's which will lie between the oldest first growth episode and the latest growth episode. So that means when we sample, this is the Bergell granodiorite, a very nice looking, not metamorphosed granodiorite in the Alps, in the southern Alps. So we have this is a real example, so we have this 650,000 years of age dispersion. So how to interpret this? Assuming that we have 650,000 years of melt present and zircon is crystallizing, is certainly not working when you start to do thermal modeling, because it's actually intruding into non-metamorphic sediments, at least at one end. So maybe some of the grains were crystallizing earlier and then were recycled, so we call them anticrysts. And maybe the last one, I don't know exactly what to do with the last one. Is this now really the last zircon which crystallized at the solidus? Or is this one which escaped to our chemical ablation process? So one of these lacking 5%, we are not sure. But we'll probably come up by analyzing several samples that we have a load of anticrysts which crystallized earlier, got transported into a higher crustal level. Then we probably have some prolonged crystallization, maybe of 300,000 years, and then we may have some residual lead loss, possibly. And so this 300,000 years of prolonged crystallization, this is a value which comes up again and again, also in modern systems, as a maximum period of time you manage to keep zircon crystallizing and the melt system alive. So in so-called hot zircon crystallization models. So anticrysts, they get transported in the magma. I showed this slide last week. So you have the story of the Fish Canyon tuff, where zircon started to crystallize in the magma, which was about 40% crystallized. And then during 200,000 years, magma got nearly solid, and then was rejuvenated by incoming hotter magma, so either just hot magma from the mantle, or the isotherms were moving up, and then got rejuvenated, so the melt fraction, the crystal fraction got reduced, grains get resorbed, dissolve, and then you end up with a melt again at something like 45% crystals, which then exploded as a explosive volcanism. So these are all anticrysts. Only the last ones you can consider as closest to the age of the eruption. And the argon age and the age of these three zircons are kind of coinciding, depending on how you deal with the offset of the decay constants. So we have to assume that all igneous rocks, they have a certain load of anticrysts. And this is also shown by modern volcanics. So Marks and Helens, we know when it erupted. So some samples, some facies or tuffs of this volcanic event, they have zircons going up to 600,000 years in age. So they stayed in the magmatic environment, probably solid. Most magmas are mostly solid most of the time. So it shows this is kind of an example of what these people call the cold storage model. Whereas the other one with 300,000 years of melt present, they call the hot storage model, which is, I think, is not exclusive, it's just different periods of time in the same magmatic system. Then we also have to deal, now we are a series of labs. There's a number 16. We claim that we are the best TIMS labs in the world, but we should also show to the community that we actually, when we analyze something, we get the same, right? Because we are using the same calibration solutions, the same tracer solutions. Now this is a cross-calibration exercise which just gets published now. This was a Bleshowitz reference zircon solution produced mostly in Geneva, which then got spiked in ETH, and then distributed to different labs, and they all measured this solution had to pass over the columns, make chemistry, and measured the 206 to 38 age. So all these data put together give a fantastic statistics. So this MSW of 1.5 is close to the ideal value, which would say that this is purely analytical scatter. So this is the top result. But when you put the means of the different labs, it looks a bit worse. But nevertheless, this value here, the two standard deviation of all values, the worst we can assume is 0.05%. So that means that any scatter beyond this value, 0.05% of the 206 to 38 age, is natural. That is not anymore analytical. And this is, I think, an extremely good result for the community. And all the rest, this is just destroying our wonderful analytical performance, because this is now geology. We have to interpret on the basis of our data sets we assemble. And just one single word to data presentation. Some of you may have wondered why this is not showing up. So we have abandoned the decay from 235 uranium to 207 lead. Why? Because when we measure now a very small zircon grain with a certain radiogenic to common ratio, we have to correct for the common lead, for the isotopic composition of the common lead in analysis, which is mostly blank. And the blank is controlled over a period of time, repeatedly measured with precisely with the spike, with the 202, 205 lead, 233, 235 uranium spike. So we know also about the variation of the isotopic composition of our blank. So we can not only put values, isotopic values for the blank, but also the variation of this value. And when we now move this point within these uncertainties here, so the critical one is the 207-204 ratio, then we can easily move to a discordant place to the right of the position, to the right of the Concordia, or to a discordant position, inversely discordant position to the left. So this H here has no more importance. It's only this date, the 206-238 uranium date, which bears H information. And of course, when you deal with old rocks, you would then at some point switch over to the 207, 206 lead H, where this discussion is not anymore important. Okay. So this was IDTIMS. I think the biggest disadvantage is the bulk grain. We are analyzing grains which are complex, and we don't necessarily know what is the complexity. And with laser ablation ICP-MS geochronology, I think there is one step. First step, simplest, is absolutely essential. This is the imaging. So my message is that first you have to do a lot of imaging and come up with an idea how these grains formed. How many growth phases, how many resorption phases, is there inherited cores or not? How many secondary overprint phases you see, and then you make a kind of a hypothetical growth history, and then you decide I shoot zone 2 and zone 3, and I will be able to consider them together as one. And then you stick to this. So when you look at these examples here, this is clearly a core, but this core has been totally replaced by some secondary stuff. So this would be number 1, but overprinted by a secondary process. This is also a core. Maybe 2 in 1. Huh? This is obviously, as I didn't consider to be a core because it has no rounded surface. This I consider to be 2, so this is an internal sector and oscillatory zone, like here. So it's not always easy and straightforward, but I try to come up first with the model and then shoot the holes. The second important point is the standards. So laser ablation ICP-MSs are relative to a standard. So why do we need a standard? Actually, we need 2 standards. So we have a primary standard because what we measure on our fantastic mass spec is nothing else than an intensity ratio, 206/238. And any mass spec is doing wrong. You know, a mass spectrometer is always measuring something which is wrong. It has a mass spectrometer fractionation effect, so we need to calibrate this. So we need to calibrate this using a primary standard. We know exactly the H, and this H has to be an IDTIMS H. And then we establish between this ratio and this ratio is an offset, and this offset is the beta, which is called the relative sensitivity factor. It's all fine. Every lab does this. But then we take an unknown sample, we do the same thing, but we do this by assuming that the beta is the same. With this unknown, who has a different age, different uranium concentration, different trace element composition, we assume that this has the same beta as this one. There are several problems with this. The beta is varying from day to day, depending on machine parameters. Sometimes we don't know, depending on the weather. temperature, the mood of the lab technician. But we need to have representative day-to-day statistics of beta. And this we do by using a secondary standard. Again, a reference material. We know exactly how old it is from an ID-TIMS age. I only accept ID-TIMS ages, right? Because we need this then to determine how much this beta is varying per day or between 2 sessions or between 4 sessions. And this variance of this beta has to somehow be propagated onto our unknowns, somehow, which is not trivial at all. This is an example of my own work. So these are 4 sessions I did in Lausanne. This is the lab of Alexei Ulyanov in Lausanne. So we measure this all based on GJ1, 600 million years something, as primary standard, and then Pleshovitz as a secondary standard. So these are 4 sessions over 6 months. So the maximum dispersion of the youngest and the oldest is about 1%. So the age of the secondary standard is actually only accurate for session 3 and session 1. Here we are much too old, so our unknowns will be 1% too old. Here we are too young, our unknowns will be too young, right? So we have to somehow propagate this fact onto our unknown age. But how? So we can do the simple way. So we take the uncertainty A is the uncertainty derived from data scatter from your laser, from your sample. The beta would be the data scatter of your secondary standard, which is actually not so bad because it's there's somewhere an age. Yeah, here, yeah. We are in the Zuckermill range. So we do not really increase the uncertainty so much by this. But the more important question is the accuracy. So here we are ending up with an uncertainty still of plus minus 0.3%, but we know that actually our dispersion, our inaccuracy could be 1% or even more. So how would we do this? The reason for the variation of this relative sensitivity factor is the so-called matrix. Everybody speaks about matrix effects, but what is this actually? Matrix is the trace element composition of zircon. So we have a series of ions which are replacing zirconium 4+. Some of them are 4+, some of them have different valence, mostly the rare earth elements. And then we also have some ions which are replacing silicon on the 4+ side. So also here we have some offsets in valence. We have to compensate. We can compensate with weird elements like 2+, 3+, but also 5+. There's quite a bit of niobium in some zircons. And it can also be compensated by H, hydrogen or OH groups. And then we have radiation damage, which is a completely different thing. We'll come back to this. So any zircon is naturally heterogeneous, shows a variation in trace element content. So our standard, the standard or the standards for primary and secondary, and our unknown, they should be perfectly identical. Be perfectly identical in terms of trace element concentrations, because otherwise you will have some lattice effects which are different between standard and unknown. It is theoretical. Huh? So we can actually quantify this matrix effect empirically. Has been done a few times with a horrible outcome. So this is just one example. You take 5 reference circles, you take 1 as primary standard, measure 4 as unknowns, then you take the 2 as primary standard, measure the other as unknowns, you do a round robin test. So Klötzli came up with a maximum of 7% variation. 7! So you see your new Proterozoic granites plus minus 7%. This is what you can say as an accuracy, but it's mostly better than this. So it's a bit too pessimistic. But of course, the beta 1 of these 5 reference circles, beta 1 is not equal to beta 2, not equal to 3, not equal to 4, not equal to 5. This is clear. So how to deal with this? So, two conclusions. No single analytical chemist in the world would rely on a one-point calibration. Analyzing strontium in carbonates or in waters from a lake, you have at least 3 standards. You make your calibration curve with atomic absorption, with photometry. But we think taking one is fine. Eh? GJ1 is the best. Okay. So realistically speaking, our accuracy is not better than this. And it's not 7% what Klötzli wrote, it's 2 to 3. And we have derived, with lots of disagreements, we arrived at the conclusion, Alexei and me, that we'll take a very pragmatic approach to this, because between the lab, the ICP lab in UNIL, in the Lausanne, and the IDTIMS lab in Geneva, we have done a lot of double dating. And we decided, okay, we are never worse than 1.6% off. So the mean of the laser date with the IDTIMS. So we take this as the maximum inaccuracy we can accept, plus minus 1.6%. So this is kind of our maximum estimate, which we cannot propagate as an uncertainty on our own. There is no mathematical way to do this. Just we have to know. We have not to forget this. And then there is one aspect, the radiation damage. So this is a very simple diagram. This is our GJ1, for instance, primary standard. You ablate 10 seconds, you get a certain depth. And this is the ablation efficiency. It's quite a nice Zircon. Homogeneous, not too. It's not the decay damage is not too much. Then you take your unknown, which is heterogeneous, has maybe a higher degree of decay damage. So within the same 10 seconds, you get a deeper hole. So the ablation efficiency is higher because your lattice is more damaged. So here you have a smaller degree of downhole fractionation, here you have a higher degree of downhole fractionation, because you fractionate your uranium lead ratio as a function of depth in the laser hole. So this also participates in what we call the matrix effect. And actually, this depends very much on how you correct for fractionation. So when you just take an average of this and an average of this, you amplify your matrix effect. So we have a matrix effect already because of the trace element concentration, and in addition, you amplify this with a factor due to the differential ablation efficiency. And this could be easily removed to some extent by just annealing the zircons. Not chemical ablation, just annealing. Muffle furnace, 950 degrees, 2 days. For standards and unknowns, you get rid of some of this. And what this means here, when you use the standard iolite, for instance, you use for uranium lead data treatments, it's just taking an average, which is considered to be amplifying your matrix effect. Other people, they calculate some model, back calculate the fractionation to 0.0, like the argon people do, and use this. And there you get rid of this effect of differential ablation efficiency. But I think empirically, this would be the easiest to do. And there are many, many labs doing this nowadays. The next question is, of course, could we actually mitigate this through chemical ablation? So this is a study by Fonquat et al. Where is it? This one here. So he made the effort to analyze the same zircon population untreated and then using chemical ablation. It's clear that the chemical ablation is removing, it's clear that the untreated grains, they tend to much lower ages, they have lead loss and also points which are sometimes higher up. And the chemically braided data points, they kind of have a better statistics, less variation, and give a better range. Okay, now we'll show you shortly a few examples where we have data with those techniques. So this is in Peru, this is the laser ablation dates, and these are the IDTIMS dates. So here we see that the laser ablation age, the mean is very imprecise and is too old, not too young, like we would kind of think it should be. So here is too old, but it's too precise, inaccurate, and too old. And one message here is definitely you should never ever try to take the oldest and the youngest and make this spot ages and make this the duration of Zircon growth. Some people try to do this. This is, I would say, in the light what I have shown you so far is fundamentally wrong. This is the second example. These are laser ablation data sets and IDTIMS from Bajo de la Umbrera porphyry deposit. So here we have laser, a set of laser dates. Here we have, for the same porphyry, another set of laser dates which are too young. These are the IDTIMS dates are here. Same for another porphyry, too old, here is too young, here is too old. So this is our effect of differential matrix. And what the people have done on the basis of the laser dates here, they have said, okay, our magnetism lasts for 1.35 million years. And then they have done IDTIMS, and then it came out that this 160,000 years. So the duration of your magnetism, which is important to understand because it's a porphyry copper environment, is essential. So laser ablation dates are not suitable to estimate the duration of a geological process accurately. And I'll give very shortly another example. So these are all untreated zircons, scattering over some million years. They're all concordant. Let's say that there's a molasse sandstone. Let's say this is detritus from Adamello basalt in northern Italy. So when you take all together, we get to these, so a too high MSWD value. And now we have to question which are the explanation for this excess scatter. How old is actually the Adamello basalt? Because we assume this is detritus from the Adamello. And what is the maximum depositional age? So question one is easy, lead loss, maybe only this, maybe the whole cluster here. Maybe this is an unrecognized old lead component, a leftover from incomplete dissolutionary precipitation, plus we have some analytical scatter. How old is the Adamello basalt? So there are several approaches. Some people still take the youngest grains. I think it's complete nonsense. We are sure these are untreated zircons. We are 100% sure there is lead loss. Okay, forget about this, not acceptable. Youngest statistically valid population of N bigger 3, widely used for maximum depositional ages of sediments. How do we know whether they have lead loss but they don't have any more? So there's no guarantee that this is not a lead loss cluster. And then there's another approach here, the youngest mode of the kernel density, which just takes an average here from all these points, but we know that we are mixing analytical and natural issues. And I would say this is, even though this is sometimes coinciding with an IDTIMS age, I would not consider this to be a viable procedure. And what is the maximum depositional age of this sandstone? Again, the three same approaches. It's very difficult. I even don't want to comment on this. And now, the worst thing, I was of course cheating. This is not the sandstone. These are 4 distinct intrusions in the Adamello. I just put the data together. Clear cross-cutting relationships between them. So actually what means that the basic fundamental conclusion of this laser ablation technique cannot resolve time beyond its inherent imprecision and inaccuracy. So the structure of this data set, we cannot resolve with laser ablation. We can resolve it doing mapping and then dating the different plutons. And this is an example from the alpine basement. You know, 800 million years, 200 million years, you would not come to the idea to postulate here we have 600 million years of melt present. We have crystallized zircon, hot origin, 600 million years. No, of course we have done. There's about 150 years of geology done. There is the Cadomian orogeny, so these are detrital zircons. There is Generian is now called orogeny 450, the American orogeny. And in addition, we have always lead loss, we have always mixing with all the components, and this making up this data set. And most of the dates are actually concordant. So laser ablation data are too imprecise to resolve the complex geological history of this. Okay, so I got more negative. Huh? So we have seen the implications from all this, that chemical ablation additives dates beyond 0.05% of the variation of the 206 to 38 uranium age are not analytical but natural. I would strongly insist on the second point, that you do very careful, precise, high-resolution laser ablation, CL imaging. You should not overestimate the precision. And importantly, we should not use laser ablation dates for durations and rates. It's wrong, because the laser ablation dates are not made for this. We can approximate an age and emplacement, but no rates, no durations. So, to end up positively, so what could we do to improve this? Maybe somebody who comes with a chemical background, maybe there is a way to get to multiple standard calibration procedures. I really don't know how. So, well, maybe. We should consistently apply thermal annealing, what I now do consistently, especially except when I forget it. And we should maybe put some effort in trying to evaluate whether how we could modify chemical ablation procedures, also to be adapted to laser ablation dating. We should from time to time check alpha decay related lead loss via Raman spectroscopy. I don't know whether you have a Raman here. It's easy, you don't need any sample preparation. And most importantly, you need to have a chemical ablation additives lab to from time to time check the accuracy of your laser dates. This is absolutely essential. Okay. Obrigado.
Thank you very much, Urs, for the excellent presentation. Perguntas? Aproveita, Marielle.
You showed a diagram of the fish canyon of zircons, and it showed like two groups of different dates, and you said one of them reflects it's closer to the age of eruption, and the other one is older. I didn't quite get, is there an interpretation that can explain this process of two different dates? What's the phenomenon responsible?
So there are not two different dates. These are all zircons which crystallized over 450,000 years, right? This looks like continuous growth, and this diagram. This is a model using modal mineralogy and assuming fractional crystallization only, and is mainly dominated by the fractional crystallization of titanite. And during all this process, zircon the melt was saturated for zircon, and zircon was crystallizing. It's several assumptions, but we have for sure zircon present in a hand sample which has apparently grown over large periods of time, over from 0.6 to 0.2, 400,000. Okay.
In this work, they have used the composition of zircon to estimate.
Yes. Yeah.
The degree of fractionation.
Yes. You analyze. So this is done by analyzing the chemical composition of the dated grains. So the TIMS TEA. Yeah. So modal composition of the rock and KD values which are published in the literature and so on. Yeah. And melts probably, or melts rhyolite.
Marielle?
Hello. I I'm curious about chemical ablation. Chemical ablation is a technique for zircon grains, right?
Only use it for zircon, chemical ablation.
Chemical
Yes.
abrasion. Chemical abrasion is used only for zircon. Yes.
Yes, but do we have another technique similar to another grains like badelites?
Okay. No. No chemical abrasion. There are some people tried chemical abrasion with badeliite. So when you deal with badeliite, you know this it was a total failure. And there are some people in the world who try to write up what they know in a series of papers about badeliite. But what we think to know is that badeliite does not show decay damage. Because the zircon, the alpha decay in zircon is damaging the lattice, whereas in badeliite is behaving similarly like monazite. It's kind of the lattice is tolerating this, and when the degree of ion the ion movement in the lattice gets too large, the badeliite is changing from the symmetry. So it's not just accumulating decay and get net damaged. It's changing the symmetry. So we are not 100% there yet, but we think that there is no way to use a similar abrasion process for badeliite, unfortunately.
Also, you said the duration of the lifetime of magma chamber of granite region. We should not rely on laser ablation data, but most of the data we have nowadays are laser ablation.
Yeah.
The first time something was done with TIMS was for Tuolumne in Sierra Nevada.
Mm-hmm.
They said 10 million years
Mm-hmm.
would be, I guess, a good estimate. Are there any other examples of such a large time scale for construction of people that you know from TIMS data? What's your opinion on the normal duration of magma chambers?
Yes, so
Geneva, for instance, is
yeah, I understand. So Tuolumne is a gigantic basalt, is Pluton in an even more gigantic basalt. So of course you assembled the first people, they realized that it's not homogeneous, so there are portions of melt which have different age. These so phases of the Tuolumne basalt. And there has been TIMS work done since. I would have to look up. So by Americans, people from Princeton and others. And I think this is not the question. I think the basalt can easily in place over 10 million years, but the single melt batch will have a very restricted lifetime. So the example I showed in Iguazu, this is a very small thing. So there we can kind of see, okay, this took 200,000 years, 300,000 years, 200,000 years. With Tuolumne, when you do the work at the same scale, outcrop scale, I think you will probably get the same. So small batches, which are maybe compositionally not too different, but the zircon may show a more complex history. I don't think that there is.
Yeah, they show reworking on cannibalism.
Yeah, cannibalism. Well,
so there's life there.
Yeah. Well, cannibalism is one of the key words.
Autophagic.
One zircon.
I have one question. This cross-check you have been doing between IDTIMS in Geneva and laser ablation in Lausanne. The most appropriate way to compare the different techniques, it's you cannot compare individual dates from in situ data with the TIMS. If I have the control that exact grain has been dated by laser ablation and TIMS.
Mm-hmm.
I can only compare the weighted mean ages from laser ablation.
Yes, of course, yeah.
Yeah.
But what you can do, you can make your zircon mount, image it carefully, and then you do the laser work, and then
Yes, remove the grains.
and then you remove the grains, and this is what.
And then I am able to compare individual dates. That's my main point.
You cannot compare a single a single spot edge with the IDTIMS data of the same grade, because the single spot edge has several percent of uncertainty.
But even though I'm just concerned if I just have a set of grains from the same sample, if I have some bias in the sampling, you know, and this would have an effect in the final age, you know what I mean?
Absolutely. We have this, in both techniques, we have these very subjective steps. We select the zircons for both, and when you do laser first, then you select the youngest. For IDTIMS, or maybe you take a selection, not only the youngest, but to compare the single spot age to the IDTIMS age, they will probably always overlap. So let's say like this.
Yes. I mean, they would overlap just because of the high uncertainty of the laser ablation.
Hello. Are we close enough to the theoretical limits of this technique? I mean, there is still space for work to improve.
So do you speak about IDTIMS, I guess?
Yeah.
Yes. Yeah, well, there is incremental improvement all the time. You know, we have in Geneva, we have mass specs of two different companies. So the isotopics, VGGV isotopic side, invented a few years ago this new type of resistors. So atonas, which are capacitor-based amplifiers, and not anymore resistance-based. So this was an improvement, I guess, to some extent, which does not mean that precision you get is better from one or the other. It's just no. I think there are some incremental improvements, but I don't know where is the what is the let's say like this: precision is not anymore a problem at all. You know, the problem is to understand the natural system we are analyzing. So we can get precise, but it doesn't change the fact that we have these 600,000 years of antichristic zircon in a sample. So I would say mass spectrometry will of course improve, and we want to get away of multipliers. We want to measure always this high resistance or high sensitivity Faraday cups, but this will not be the total revolution of the method. What is definitely very wishful is that we have at the moment that in TIMS, you know, we have a filament. We put our sample on. We have an ionization rate of what, 7-8% maximum. We would like to have a 98. That's the main limitation. So getting away of multipliers, this we can do tomorrow. We have everything, you know, but getting away from rhenium filaments, this will take a bit more.
So that's the next step for high precision improvement.
And you know, the organic chemistry, when I studied, I had some organic chemistry, and there was a famous mass spectrometrist in Bern. He was at the forefront, and I met a student of his recently who is retired also, and he said, oh yeah, we gave up with these magnet sectors already decades ago. You know, nobody in organic chemistry is using magnets anymore for mass spectrometry. Now there is such a moment where one of these two companies comes up with a completely new way of ion collection. So maybe orbit traps. Maybe, you never know. 20 years from now, we look at these mass specs you see here. Oh yeah, 20 years ago we still used magnets. Maybe, maybe not.
Mais perguntas? Tem alguma no YouTube? Não. Então, vou encerrar. Falta ser? Não. So, thank you so much again, Urs, for your talk. Obrigada a todos pela presença.